All right, well, it gives me great pleasure now to present this year's CEDAR Prize Lecture to Professor Jeff Forbes from the University of Colorado. Jeff has been a real friend to Aeronomy and to CEDAR over the years. When his name came up for this award, I was sort of amazed that he hadn't already won it. And in fact, in checking backward, he hadn't, but we can perhaps be forgiven. It maybe is the only award that our community offers that Jeff hasn't already received. There's not sufficient time to go through Jeff's list of accomplishments and awards and still allow him to give his lectures, but I will try to summarize. Jeff received his PhD from Harvard in 1975, reputed to be a pretty good school. After that, he held joint appointments, professorial appointments at Boston University in electrical and mechanical engineering before moving on to the Department of Aerospace Engineering at Colorado, where he's had a very distinguished career holding an endowed chair and until recently also being chair of the department. Jeff has served on a veritable alphabet soup of important committees and panels, holding leadership positions and really shaping the way that our community has evolved. He's held many important leadership positions. He was the CEDAR chair not so long ago, one of the Time PIs, and most recently he was the chair of the AMI panel of the Decadal Survey, which is perhaps the most important panel we have for informing the direction that Aeronomy is going to take, at least with respect to our relationship with our agencies. Jeff is a fellow of the IAA and the AGU, and he has at least 240 refereed publications. Many of them are seminal publications. I'm sure most people in the room have cited very many of them. And something I didn't know, he's a retired lieutenant colonel in the Air Force Reserves. So not something that many of us can claim to be. So I'm very pleased to be able to, on behalf of the steering committee, offer this award to Jeff, and I'm really looking forward to his presentation. So thank you, Jeff.
Okay, so my talk is on atmosphere-ionosphere coupling by tides and planetary waves. So as Dave pointed out, I did my PhD in 1975, and the title of my dissertation was Atmospheric Solar Tides and Their Electrodynamic Effects. And I did the Dynamo, the equatorial electrojet, and so forth. So I've been doing this stuff for 40 years, almost. A point that I hope will emerge at the end of this talk is that we've learned a lot since 1975 on this topic. And for the students out there, there's a lot more to be learned, a lot of unanswered questions. So I have a little bit of a subtitle for my talk, and that is, how do interactions between the sun, the moon, and the earth introduce complexity into the ionosphere-thermosphere system? And before I go on, I'd like to recognize my colleague Xiaoli Zhang for assisting me in the preparation of some of the figures in this talk, and for my students, Mac Jones, Federico Gasparini, and Riham El-Hawari. I'll be highlighting, in the context of demonstrating how much we've learned. Obviously, I can't do that in a short period of time, but I'll give you some very recent results that have just appeared in the literature or will appear in the literature soon. And they're very much, I'll be quoting my students, and a lot of the stuff I'm showing are my students' work, current work. So let's see, do we have a laser pointer? I'll use my cursor. Okay. So, oh, thank you, Shinchao. A LiDAR person giving me a laser pointer. That's great. The lower atmosphere communicates with the upper atmosphere and the ionosphere through the generation and propagation of waves. And the waves consist of gravity waves that are much, small scale, minutes to hours periods, tens to hundreds of kilometers wavelengths, and also in the form of tides. The atmosphere is rotating, and the sun is rotating with respect to the Earth, and the absorption of solar radiation projects onto periodically in time, in local time. So the subharmonics of that are 24 hours, 12 hours, 8 hours. And because the Earth is rotating, there's also periodicity and longitude. There are also planetary waves generated. So the gravity waves are generated by convection and topography, number of other processes. The tides are generated by water vapor absorption in the troposphere, ozone absorption in the stratosphere. And then we have planetary waves. Some of these are actually resonant oscillations of the atmosphere. You go through the mathematics and show that they should have an infinite response. They don't have an infinite response in the real atmosphere, obviously, but you see these waves in the atmosphere too at periods of 2, 5, 10, 16 days. And then there are other planetary waves generated by instabilities and so forth. And then on the way up to the ionosphere, these waves interact with each other. So they undergo nonlinear interactions between the tides and the gravity waves and the tides and the planetary waves and so forth. So we have a whole spectrum of waves propagating up to the base of the thermosphere and growing exponentially with height on the way. So they're getting really large when they get up to the mesopause and a little bit above. Now, I'm not going to talk about, I didn't mention also that we have waves getting generated in the aurora region and propagating to lower latitudes, propagating into the other hemisphere. We currently don't know what the implications of those waves are on the mean state of the ionosphere-thermosphere. I'm not going to talk about those. And these gravity waves are very important. They can go up and, we think, possibly seed instabilities that lead to spread F and so forth in the equatorial region. I'm not going to talk about those either. These are outside of my domain of knowledge, and there's so much to be learned about those things that it's, well, let me just go on. And then the gravity waves that are generated here and deposit their momentum in the upper atmosphere. They create turbulence and mixing. They interact with the tides. I'm not going to talk about those either. Okay. Gotta focus, right? So what I am going to talk about is some of these tidal processes. So some of these tides penetrate all the way up until orbital altitudes. We actually sense those signals from measurements on the Champ and Gray satellites. They also introduce composition changes, and they also generate electric fields. So the ones that do propagate up can move ionization. The winds associated with these waves can move ionization along field lines. And the field lines are inclined with respect to the horizontal, and there's a declination effect in the east-west direction and so forth. So let me just do a little bit of simple review on what the Dynamo Effect is. Now, here's a magnetic field line over the equator that peaks over the equator, comes down at low latitudes, middle latitudes. And in this E region, the gyro frequencies of the electrons around the magnetic field line are much greater than the electron-neutral collision frequencies, okay? So they stay bound to the field lines. But if a neutral wind comes along, it can move those ions with respect to the magnetic field line, because the ion-neutral collision frequencies are of the same order as the ion gyro frequencies. And so that produces a current. Now, if you look at the really simple Maxwell's equations, steady state, you see that current has to be non-divergent. So how does that happen? Because the current that we created is not non-divergent. So here we have the expression for the current in terms of the electric field vector, and this is the conductivity tensor. And here we have a global electrostatic field and this is the neutral wind cross B electromotive force. So what happens here is, in order to maintain non-divergent current everywhere, an electrostatic field is set up everywhere to make the currents non-divergent. And so here's our little electric field here that's been set up. And oh, by the way, these magnetic field lines are equipotentials. And so this electric field just maps right up into the F region. And even though the electric fields are generated in the E region, their greatest effects are in the F region, where they produce now E cross B drifts, because at these altitudes, both the gyro frequencies of the ions and the gyro frequencies of the electrons are much greater than the collisional frequencies. And so an electric field there produces an E cross B drift of the plasma. And if you have an eastward electric field at the equator and a northward B field, you produce an upward drift. And we all know the fountain effect that produces the equatorial ionization anomaly. And this is the basic process that produces that. And so you can imagine that this spectrum of waves that's coming up, all with associated wind fields, all with different periods, all with different zonal wave numbers and longitude, this spectrum of waves is imprinting itself on the ionosphere in the F region through this process. So we have temporal and longitudinal variability in the F region that's due to the waves coming up from below and producing these electric fields. Now, there's an evolution of the spectrum. So the waves are encountering molecular dissipation around 150 kilometers. They're reaching their peak amplitudes there, conveniently right where the dynamo process is occurring. And there's a filtering of that spectrum. And the longest vertical wavelength waves get all the way up to the F region. And those waves can actually transport ionization along the magnetic field. And so we have a northward wind, perhaps inclined with respect to the magnetic field. There'll be a component along the magnetic field line. The same way, if we have an eastward wind and there's a declination, east-west declination of the magnetic field, there'll be a component of the wind that pushes ionization in that direction. So we have the part of the spectrum down in the E region that's producing electric fields and transporting ionization in the F region perpendicular to the magnetic field, and then we have the part of that spectrum getting up and moving ionization parallel to the magnetic fields. So this is a level of complexity in that process. So in particular for the students here, I wanted to draw attention to the CEDAR strategic vision. And if your students haven't read this document, you really need to read this document, because you can really see where your research fits into the big picture. And that's an important thing to do. But I did note that just a simple search of the document, complexity is used 45 times and complex is used 66 times. So the underlying theme of a couple of underlying themes in this document. One is the atmosphere-space interaction region, which is really where the dynamo region is, more or less, and more, but also complexity in terms of understanding the complexity of the system, the ionosphere-thermosphere system. So I'm only talking about atmospheric and tidal and planetary waves. So I'm only looking at a very narrow piece of the whole picture. I'm forgetting about gravity waves, I'm forgetting about aurorally generated waves, and I'm forgetting about all the other stuff that introduces complexity, but just focusing on this little piece. So how do tides and planetary waves introduce complexity vis-a-vis the processes that I mentioned earlier? Well, first of all, that spectrum is not steady. It's due to tropospheric processes that are changing on a day-to-day basis. And on a weekly basis, seasonal basis, and interannually. Secondly, there's a longitude variability of that spectrum. It's not the same at all longitudes. And again, there are wave-wave interactions within the spectrum. We know, we've even seen from models and observations that two tidal components interacting together will produce two other tidal components, and we can actually see those all in the data. Another way that complexity is introduced by the solar modulation of the ionospheric conductivity. So I said that J was equal to sigma times E plus U cross B. Well, U has a lot of complexity. Those are the winds. But then there's the conductivity, which depends on the solar flux. The EUV flux, which we all know varies from day to day, and with certain periodicities like 27 days, 13 and a half days, and so forth. And then the last part is the global magnetic field configuration, and I already mentioned that to you a little bit, but there are longitude, latitude variations in inclination, declination, and the displacement from the geographic coordinate system. So the processes I mentioned earlier, these things introduce complexity into the system. And so I want to show you an example of this, and this is from the work of my student, Federico Gasparini. It's appeared in GRL. This is really a simple illustration of what I'm talking about. So we have plotted here in blue for the year 1990. This blue curve is the horizontal magnetic field variation observed on the ground at Huancayo, Peru, noontime values for the whole year. We picked this year because the red line here indicates F10.7 solar flux. It has a nice, strong 27-day variation. Okay? What else did I? These are residuals from the mean, and I think I said everything I need to say about that. So we have these two time series. And remember that the delta H on the ground for Huancayo at the magnetic equator is not too affected by the local neutral winds. There are some effects, mostly due to the electrostatic field. And the conductivity is mostly affected by the solar flux, which has a 27-day variation. So let's look at the spectra of these two time series. Okay, so the red line is the spectrum of the F10.7, and the blue line is the spectrum of the magnetic perturbation on the ground. And to first order at the equator, we can say that the delta H is proportional to the height integral of the cowling conductivity times the electrostatic east-west electric field due to dynamo action of the neutral winds. That's just a first approximation, but we're going to get across the main idea here. So forget about this green thing, which is the AP, spectrum of the AP. The primary peaks in the delta H spectrum associated with the electrostatic field is this 14.77-day lunar tide peak, and two side bands, which account for the annual variation, intra-annual variation of the delta H. The primary peak in the solar flux is at near 27 days, 25.6 days. And you can see that there are several other peaks in the solar flux spectrum and a number of other peaks in the delta H spectrum. So from this simple idea here, if we have a solar flux modulating an electric field, a solar flux with a 27-day period modulating an electric field with a 14.77-day period, simple-minded approach, you can just say it's the product of the cosines. This is the modulation of the lunar signal by the solar signal, and that gives you these sum and difference wave components. And it turns out that this is, these sum and difference wave components are 1 over 9.3 days and 1 over 34.1 days for those two interaction between this peak and that peak. And lo and behold, you can find those two peaks in there, here and here. This blue line is the confidence level for the delta H variation, and the red is for the solar flux. So we can find those two interaction peaks. Turns out that if we consider L1 and L2 in here, and the 1, 2, 3, 4, 5, 6 spectral peaks in here, then almost all the other blue peaks can be identified with those interactions. Okay? And so what does that look like in the time domain? So if we take the original data, reconstruct it with all the peaks with greater than 90% confidence level, we get this blue curve. And if we reconstruct that time series using only the solar rotation and lunar peaks, S4, L1, L1, L2, we get this red curve. And we can account for 59% of the variance with those peaks. Now let's take into account all the secondary peaks that were produced by the interaction between the solar flux and the electrostatic field. And we get a pretty good match to the curve. In fact, we capture 86% of the variance is accounted for. Okay? So that's what I'm talking about. That's what I'm referring to as complexity in the simple example. And really what's happened here is the solar radiation flux from the sun, the gravitational field of the moon, and the magnetic field of the Earth have all interacted together to produce complexity in the ionosphere. And that's the theme I want to get across. So now imagine, this was just with one little spectrum and one little location and one lunar tide. Now imagine this complexity expanded globally, and including the full spectrum of diurnal and semidiurnal tides and planetary waves, modulated by the complexity of the magnetic field, modulated by solar flux influences on the conductivity, and compounded by the periodicities associated with recurrent magnetic activity. So this is a sort of a warning signal. For 1990, if you looked at this is 2009, so this has to do with my next plot. If you look at a typical spectrum for KP, quite often you'll find peaks at 13.5 days, 9 days, 7 days, 6.7 days, all subharmonics of 27 days. These are all due to recurrent magnetic activity. Now, the 13.5 days has to do with the way that the heliospheric current sheet is tilted, but the 9 and other peaks are due to the distribution of coronal holes on the sun and how they produce high-speed streams that interact with the Earth and produce recurrent magnetic activity. The main point of this is you have to be careful when you're analyzing the data, because there are other signals that look like planetary waves and are not. 9 days, 13.5 days. Okay, so I thought as an example I wanted to look at some CHAMP data. And so CHAMP was launched in 2000 into an almost circular near-polar orbit with an initial altitude of 454 kilometers. It carried accelerometers that measure neutral winds, neutral densities, cross-track winds, and it had a Langmuir probe that measured electron densities. So this is a snapshot from one day, day 332 of 2009. I'm going to show you a movie that covers the whole year. But this is the ending, and keep in mind that the CHAMP orbit is near polar, right? The Earth is rotating once per day beneath that orbit, and the orbit is more or less fixed in space, and During one day, it samples about, with a 90-minute period, samples about 14 or 15 longitudes. Okay? But at two local times, one on the upswing and the other on the downswing of the orbit. So here's a plot for one day, latitude versus longitude, of the ascending part of the orbit, which is near noon, and the descending part, which is at midnight. This is the magnetic field, magnetic equator here. And you can see, for instance, here you can see 1, 2, 3, 4 peaks here. And notice that I'm not mentioning DE3 anywhere in this talk. No tidal nomenclature. But we know what those four peaks are. They're actually related to the land-sea difference at the surface of the Earth, which modulates in the latent heat release from convective clouds that produces the tide that actually went up and created the four-peaked electric field that you see the response to here. And down here, in order to better emphasize the middle latitude peaks, and a little bit to, I took the residuals from the zonal mean. So these are the residuals from the longitude mean down here. And this is the movie that I'm going to show. And I just wanted to give you an impression of the day-to-day variability of our ionosphere. Okay? This is a very limited view, though. Keep in mind that we're looking at a local time that changes on the ascending part of the orbit 24 hours and 260 days. Okay? So just take a look at this, and this is what we're seeing here is complexity in the system. Okay? We're seeing the result of all those waves propagating up, generating electric fields with longitudinal and temporal variability. And in some places, winds pushing ionization along field lines, and maybe even producing composition changes that are all resulting in this day-to-day variability, which is quite substantial, right? When am I finished? 9:30? Oh, okay. Good. You know, taking the residuals from the zonal mean also help to show the nighttime results too. And you can see the residuals are quite large. The scale here is from minus 50 to plus 150%. Minus 50 to 150%. So these changes are large, and they're changing a lot from day to day. Okay? That's the point I wanted to get across. Okay. So actually quantifying the variability is not so easy. A quick and dirty thing that one can do is, for instance, for the whole year, you can take a two-dimensional spectrum of the waves, of the data. I've broken it down into 2-month periods because you lose some of the stuff if you do it for the whole year. And so here's the spectrum. This is zonal wave number from -6 to +6. And this is periods in days, from 3 days to 20 days. And this is minus 40 degrees. So this is ascending 21 hours approximately. This is descending 10 hours, 10 or 11 hours approximately. And this is minus 40 degrees, minus 20 degrees, the equator. So this is nighttime, daytime, essentially. And so what you can see here is that, first of all, there are distinct peaks. Second of all, there are eastward and westward propagating waves in here. So the negative zonal wave numbers are eastward propagating, the positive ones are westward propagating. And there are significant differences between day and night and with respect to latitude. Additional complexity, right? And so, for instance, this one here, this is a 12-day wave eastward propagating with zonal wave number 4. And this is a 6-day wave westward propagating with zonal wave number 3. Now, if you look at the spectrum of waves that's coming up from below, it doesn't look a lot like this. The spectrum is being modified by the solar flux and the magnetic field configuration and so forth. So it's going to be a real challenge to deconvolve all this, especially since we can't get any tides from this experiment. You go taking into account day and night data, it takes 130 days to cover 24 hours of local time. What are you going to do with a 130-day mean tide? You can't say anything about its modulation by a 5-day wave. So it's a real challenge. So you might want to invoke a first principles GCM and maybe do some experiments with it. Let's modulate the GCM by a 27-day wave and see what happens. So I just wanted to discuss a little bit about observational strategies for this. And it sort of leads into my talk later today, both my talk and Rob Pfaff's talk and Thomas Immel's talk. So without measuring several local times simultaneously, we cannot extract tides on a day-to-day basis. There are methods that we can use to approximate that. And moreover, we can't determine to what degree the planetary wave periodicities in the data arrive from a planetary modulation of a tide from a planetary wave itself. So if we see a spectral peak there, that could be due to a 5-day planetary wave, but it also could be due to the 5-day modulation of a semi-diurnal tide. And in that data, we can't tell the difference. And again, there are ways that we can get some hints. But so we need to sample multiple local times and longitudes each day at a given latitude in order to deconvolve that stuff. So let's imagine if we had 3 satellites in polar orbit. What would that give us? So these are supposed to represent the satellites. This going up here and coming down here. So we look at observing I forgot the name of this projection. Molweds, I don't know, something. This is the whole Earth, not just one side of the Earth. And so this is one orbit going up and coming down. And this one going up and coming down here. And then there's one that is going up here and going down both sides. Okay, so there's 3 satellites in this 6 tracks here. So now, assuming the satellite was measuring on both day and night sides of the Earth, we'd have 24-degree longitude resolution, because every day the Earth would rotate once beneath this pattern, and we'd be measuring 6 local times and longitudes, 24 longitudes in one day. And that would give us a zonal wave number spread of plus or minus 7. So that's pretty good. We could get 6 local times, we get a mean, a diurnal, and semi-diurnal. That would about do it, I guess. But we don't have this at all. But we'd like to have it. So how would this work using ground-based sites? Just for laughs, let's see what that would do. Because a ground-based site sees all local times every day, but only at a single longitude. So let's suppose we had 30 ground-based sites, conveniently all these little ellipses that add up to 30. Now we only have 60-degree longitude resolution. And we could only get zonal wave numbers between +2 and -2. And this could be okay for some planetary waves, not for the 2-day wave. That has a zonal wave number of 3, but there are some other good planetary waves that it would work for. And it doesn't work well for tides, because one of the most interesting tides that is involved in this vertical coupling, or two of them, are the eastward propagating diurnal tide with zonal wave number 3, and that is zonal wave number 3. So we can't get that one, so that would not be good. But we'd still get a lot of other interesting stuff. But we would get continuous longitude coverage. So in order to really do this problem from the ground, and forgetting about high latitudes where the tides are obscured by auroral physics and that sort of thing, we'd probably need about 7 with respect to longitude times 10 in latitude, about 84 sites between plus and minus 60 degrees latitude. You look at the distribution of ionosons across the Earth, and there may be maybe as many 150 or something, 120, 150. Surface magnetometers is 130 or so. So you're kind of getting close to getting some decent distribution. Okay. So as another example of complexity in the system, I'd like to show you some recent results from one of my other students, Mac Jones. What Mac did, and I'm not going to give you the full details, but some of the highlights. He has a poster on this this week. What we did was we took the TIGCM, which is a first principles model of the ionosphere-thermosphere system, and forced it with a spectrum of tides, diurnal and semidiurnal tides, reconstructed from climatology. From the CTMT, the climatological model climatological tidal model of the thermosphere. See Oberheide 2012 or something, 2011. Okay. Anyway, we know the spectrum of waves climatologically from time saber instrument measurements. So we forced the model with that climatology, and then we removed the tides and looked at the difference in the response of the ionosphere-thermosphere system. And what we found out was these are difference fields, all tides minus no tides at 140 kilometers, that there was a significant, this is zonal wind. Now this is diurnal and longitudinally average zonal wind. So it's the mean zonal wind of the thermosphere at 140 kilometers latitude versus month. Okay, so we're getting some significant contributions due to the momentum deposition of the dissipating tides in the thermosphere. What surprised us a little bit is that we also got rather large changes in the NMF2. This is the peak electron density of the F region. Okay? And so what's going on here? Well, what's going on is that the net effects of the tides have been to change the atomic oxygen distribution, the O to N2 ratio. And so dissipating tides give rise to net fluxes of momentum, heat, and constituents. Okay, W prime, O prime. Now, let me show you what we're talking about here. If you take the continuity equation for atomic oxygen, and I'm taking a simplified version here that doesn't have any meridional transport. Mac has already done the meridional transport part. and it's significant, and you can look at this poster. Now, here's the simplified continuity equation. If you look at the time constants, the dynamical time constants are shorter than the chemical time constants, above about 100 kilometers. So the chemistry is playing a secondary role to the dynamics. So I'm going to drop these production and loss terms here and just look at the effects of this. I'm going to assume that the vertical velocity consists of a mean part and a perturbation part, and the atomic oxygen consists of a mean part and a perturbation part. You throw that in the continuity equation and integrate over longitude and time. Some of those terms drop out because the primed quantities are periodic in longitude and time. You get an equation that looks like this. And this W bar, O bar represents the net advection of atomic oxygen due to the mean circulation produced by dissipating tides. So I showed you before, on the slide before, that the dissipating tides produced a net east-west velocity. Well, they also produce a net meridional velocity and a net vertical velocity, and it's a circulation system. Okay? And this term here is the net advection of atomic oxygen due to that circulation system produced by the dissipating tides. And this has been studied by Yamazaki and Richmond very recently. This term here, though, is something that we knew about from the work of Chet Gardner and Alan Liu in the context of the effect of dynamics on sodium chemistry. Okay? And they called that dynamical transport. And they were talking about it in the context of gravity waves. But here we're talking about it in terms of dissipating tides in the thermosphere. And so we get a W prime, O prime. If you forget about dissipation and mean winds in the atmosphere and you just looked at basic tidal theory, these things would be in quadrature. And the average of their product would be 0. But if they're dissipating, they go out of quadrature and you get a net flux of O due to the dissipating tides themselves. And this is the change in the O to N2 rate. This is a difference in all tides minus no tides for atomic oxygen. I can't see the labels there. There's 12%, 10%. Then we have O to N2 ratio, and then we have electron density. Something like more than a 20% reduction in electron density. Now that's significant. And keep in mind that these, as we know, these tides are changing from day to day, week to week, from season, and so forth. And so this is another level of complexity onto the ionosphere-thermosphere system produced by the tides. And the same stuff, I'm sure, applies with gravity waves and other types of waves, but I'm just focusing on, very simply, on the tides here. So I could have a whole list of the outstanding questions, issues, and challenges, but I was traveling all week, last week. These are the ones I was able to think of. So we don't know to what extent planetary waves extend into the dynamo region. There were some measurements, a few model results that suggest that they can, others that suggest that they don't. Are they assisted by gravity wave filtering? So you consider that if you have a 5-day planetary wave and you have gravity waves propagating through it, their deposition of momentum will vary with a 5-day period. So is that the way planetary wave periodicities get into the ionosphere? Or do they propagate there directly? Or do they modulate tides? Does the 5-day wave modulate a semidiurnal tide, which then propagates into the... We don't know any of that stuff. A significant part of the daytime dynamo originates from winds between 130 and 200 kilometers. And Mauta et al. Showed this in a recent paper. We don't know how the wave spectrum evolves with height. From 100 to 200 kilometers, we do not know how the wave spectrum evolves with height. And if the dynamo was created by waves from 100 to 200 kilometers, you know, we just don't know what part of the spectrum is doing what. We don't know how the planetary and gravity wave parts of the spectrum affect the zonal main state of the ionosphere-thermosphere, just like I showed for a few tides previously. And how do we measure the gravity waves, planetary waves, and tidal spectra in order to understand the fundamental wave-wave interactions? That's a big issue as well, which I tried to point out with my ground-based, space-based analogy. And relatedly, how do we measure the system in a way that enables us to understand how wave variability drives ionospheric variability? So it took us 40 years or more. I mean, my PhD thesis rested on the accomplishments of many people before me. And we've reached a level of maturity now that is exciting. But there are a huge number of outstanding questions and challenges, both observationally and theoretically and in a modeling perspective, that all you students should be excited about. And that concludes my talk.